So first step is to draw the Lewis structure. Lewis structure is going to be really important here, and all that stuff we were doing with the math is not as important anymore. If you can do it shorthand, you're more than welcome. So let me show you how to do shorthand very quickly. So I'm just going to write a V for valence and a P for probable. And all I'm going to do here is just do the valence without showing a lot of the math. So what I'm going to do is this. N nitrogen, I know, is in period 5. So that means nitrogen's going to have 5 electrons. And hydrogen's in period 1. So it's each going to have 1 electron times by the subscript 3 gives me 3. So I'm just going to add 3 for a total of 8. It's the same math you were doing. You're just not writing it out in the big long table and stuff like that. If you want to do it in the table, be my guest. Do it in the table. Remember, the probable comes from the chart on the front, which again is in your packet. So I'm going to do nitrogen is 8. Remember, most of the time it's 8. Hydrogen's an exception. Hydrogen usually uses 2 electrons. So 2 times 3 is 6. 8 plus 6 is going to give me 14. So I've done the same thing with the chart. I've just done it shorthand, right? So then I'm going to do 14 minus 8. I know. I feel like this is right. And then minus 2 is going to give me 3. That's right. So I've done the math very quickly, very shorthand, just like that. If you can do it even where you just do V equals 8 and P equals 14, that's fine. You don't have to show me it at all. I don't think you're good enough to do it without doing it at all, but that's okay. We're going to do the shorthand. So very quickly, and most of these are going to work out very normally, I'm going to draw my initial Lewis structure to have N in the middle. And like we've been doing, I'm going to do the H's like that. And if I count my valence, it's 2, 4, 6. I know I need 2 more. So I'm going to make 2 dots on the top of the end. At this point, I would pause. I would go look online and make sure that's the right Lewis structure, and it is. Okay, so now I can answer the other question. So electron geometry just has to do with the number of domains. And we remember that a domain is either a bond or it's a lone pair. So if I use my little highlighter here, and I say, if I'm going to count the domains, there is 1 here, 2, 3, 4. Those are my domains. 1, 2, 3, 4. The double pair of electrons just counts as 1. So I know I have 4 domains. With that knowledge, then, I'm going to use chart number 1. And I can pull that up. It's over here. And I look at chart number 1, and I see that if I have 4 domains, my electron geometry is going to be tetrahedral. That is the name of the shape. So after that, I just take my pen and I write tetrahedral. If you can't fit the word, you can absolutely write it diagonal, whatever you can do to fit it in the box. So that's how I find the electron geometry. Next thing is going to be the hybridization. Hybridization is just, again, the number of domains, but this time it comes from chart number 3. So I'm going to pull up chart number 3, which again I have. Oh, it didn't like that at all. Chart number 3 is right here. Okay, and if I look at chart number 3, I see that if I have 4 domains, my hybridization is sp3. Do you see this is all coming from a chart? I don't have any of this memorized. I'm just pretty much finding the right domain and then finding the right information. And if you want to kind of shorten your length here, I can also figure out from chart number 3 that the bond angle is 109.5. You can actually find bond angle from a couple of places. Bond angle is, again, the number of domains, and you can find it from chart number 1 or chart number 3, whichever one you want to use. So the hard part is going to come in when we do the molecular geometry here, because molecular geometry involves 2 things. It involves the number of domains And it also involves the number of lone electron pairs. So we just said, if you have no lone electron pairs, then the electron geometry and molecular geometry should be the same. But if we look in this particular one right here, those lone electron pairs push the bonds away. So if I use chart number 2, right here, so you need 2 things to use chart number 2. You need the number of domains, which we already figured out is 4, and you also need the number of non-binding lone pairs. Notice it says pairs. It's not number of electrons, it says pairs. So in this particular structure, I have 4 domains and 1 pair, which means if I intersect those 2 points, my molecular geometry should be trigonal pyramidal. So I just write that. Notice I have to kind of do it. So it's fine to fit in the box. It's fine if you go a little outside. Now, the last thing you have to do, last part, number 5 on the back of that instruction sheet, is you have to go back and fix your picture. So if the electron geometry and the molecular geometry are not the same, then this Lewis structure is not right. That's why you have a pencil. So I'm erasing my first structure, and I'm going to redo it. I'm going to say, I'm going to have N in the middle, and I know I have a lone pair on the top. And I know that that lone pair is pushing away very violently. It's pushing the other bonds away. So instead of the bonds being like a T shape, they end up like, almost like a little triangle, like a little tripod there. So that is my correct geometry. The electron pair here, this lone electron pair is pushing away the other bonds, like that. I don't care that they're exactly 109 degrees. They don't have to be, you don't take out a protractor or anything. All I care about is that they're not evenly spaced, because they shouldn't be, because the molecular geometry is not the same.